Hello everyone, we are Team 17 and our project was on the revision of the shoulder torque range of motion device. So our advisor was Dr. Joseph J. Sarver, and the team members include Nam, who is a biomaterials and tissues engineering concentration. Myself, my name is Hang Trong. I am focusing on medical devices and imaging. Zoe Chen, which is concentrating in biomaterials and tissues engineering, and Andrea Rockefeller, who is also biomaterials and tissue engineering. So the medical need we are focusing on in this project is shoulder stiffness. The shoulder is basically a ball and socket joint made up of three bones, the humerus, scapula, and the clavicle. Stiffness can be caused by injury, which is common in athletes, joint inflammation, demonstrated on the right side of figure 1 below, or tightness in and around the muscle around the shoulder. Sometimes even without injury, patients or athletes could have some tightness from the rotator cuff muscles, which could affect their performance. Physicians currently do range of motion tests to see what extent the patient is able to stretch their arm. The movement we are focusing on in this project is internal and external.
Arming. And what you're going to see then is a very limited internal rotation, which we'll test next. So now I'm back to neutral. I stabilize the shoulder.
This short clip shows how physicians assess and diagnose
A
patients.
little bit tighter this way, you're not going to go.
A person's shoulder moves in this way. Sometimes it gets stiff, but there's no way to measure. And subjective analysis differing from physician to physician can negatively impact athletes due to their suggesting of returning to the game and overworking their bodies too soon. So we believe that being able to measure stiffness would allow more accurate diagnoses, tracking of improvement, which is beneficial for the athlete. And so one meeting with Dr. Thomas, a potential user who is a researcher wanting to assess shoulder stiffness of Major League Baseball players, he requested that the device be packable and height adjustable to measure shoulder stiffness of baseball players on field.
Here are two existing solutions in the market. One solution is shown in figure 3. Users can put their arms on the device and try to rotate their arms, as the arrow points out, to recover their ability to rotate. But the device is not able to measure anything. It's for practicing only. The second device in figure 4 is able to measure angular displacement, but still cannot correlate it to stiffness. And you can see in the picture, the entire device is very big and solid and is not portable. So in order to get a portable device to measure stiffness, Dr. Sauer created a stone device shown in figure 5. The device consists of 4 parts: a base to support the entire device, an arm brace for users to put their arms on and rotate, a handle part for physicians to assist their rotation, and a sensor part to put an initial measurement unit, which we call IMU sensor, to measure angular displacement, and a torque sensor to measure torque. Figure 6 is a sample result of what we expect to get. The x-axis is the angular displacement, the y-axis is the torque, so the stiffness can be calculated as their slope. However, there's still some shortage of this device that we need to overcome. The device is not getting accurate measurement because of issues of calibration. Also, the device is not stable enough and will move around when in use.
Essentially, our objectives is to improve on the stability and portability of the current Strom device and to accurately measure stiffness during internal and external rotation movements of the shoulder in athletes.
So some universal constraints include being able to use the facility resources from Drexel. We had to follow a timeline to complete the project by May 25th. We had to follow COVID-19 restrictions with using the Drexel facilities. We had a team budget within $500, and we wanted to follow the ASTM standard for calibrating torque devices. Some device-specific constraints include that our device is designed for a specific user, who's Dr. Thomas. And we have volume and weight constraints because Dr. Thomas would like to be able to travel with this device, so it needs to be portable and able to travel on commercial airlines. We have a preparation time constraint, which includes the assembly, the calibration of the sensors, and then the disassembly. We also have a use time, which is the actual time it takes to record measurements for each patient. And lastly, we have to work with the existing solution.
Portability is our first requirement, where the weight of the device has to be less than 40 pounds with the maximum dimensions of 22 by 14 by 9 inches. This is because the user intends to travel with the device as a carry-on. The second requirement is that the height has to be adjustable between 25 to 35 inches. Because in order to accurately assess the patient, they must lay flat on the table, ideally a medical table, and the height adjustable allow for the user to align the sensors with the patient's elbow joint. And most tables has a height between 25 to 35 inches. The third requirement is the mechanical stability of the device, because when we received the device, the base was barely able to stand on its own, and it could not support additional weights added onto the device. So the requirement is that it has to withstand a load of 25 pounds, because an average weight of a human arm is about 15 pounds, and the 20 pounds with the 5 pounds extra is room for error. The fourth requirement is the measurement of torque over time with an accuracy of 95% at a resolution of 1 to negative 10th, 1 to negative 4th of nm. Similarly, we also want to measure the angular displacement over time with an accuracy of 95%. Finally, the last requirement is to calculate the stiffness by plotting the torque on the y-axis and the angles on the x-axis, with the stiffness being the slope of the graph.
Our solution path includes using Arduino and MATLAB. And in figure 9, you can see where the shoulder joint will be rotated, and the torque cell and the IMU will take these measurements sent as electrical signals into Arduino, where the signal will be amplified and converted from analog to digital. This data will then all be put into MATLAB, where there'll be a display of torque, a display of angular displacement, and a display of torque versus angular displacement, which is where the calculated stiffness will come from. In figure 10, you can see this is what the device looks like with the patient's arm inside of the arm brace. And the line of axis that is drawn is the axis that the arm will be rotated around. So our base design revision, we decided to redesign the base because the previous one had stability problems, which could potentially interfere when taking recordings. So we did this with 1-inch T-slotted framing, 4 stem-mounted wheels, and 8 2-inch extended corner brackets. In figure 11, you can see our base design layout that we came up with. The blue pieces were the pieces that needed to be cut and drilled, and the gray pieces were what the device already had. This was given to the machine shop where everything was cut and drilled. And in figure 12, you can see the assembled bases. So the image on top is what the device looked like when we received it. And then the image on the bottom is the design that we came up with everything assembled. The existing software. So in figure 13 and 14, you can see the Arduino setup as well as the torque sensor. So this featured an Arduino Uno, a SparkFun Proto Shield, an Adafruit 9 degrees of freedom sensor, and a FUTech reaction torque sensor. In the figure on the bottom, this was the existing MATLAB code figure. It shows a display of angle and torque, as well as a display of torque versus angle, which is where the stiffness will come from.
In order to measure torque and angle, we use these two sensors in our device. We keep the torque sensor from the previous version and change a new MNU sensor to get the measurements more accurate.
This is the video of the assembled device with Dr. Thomas using it.
I'll just kind of walk you through it. So yeah, I would take you through. Once I felt your shoulder blade kicking out on me, I take it to there, and then coming back, I feel your shoulder blade move, and then go again.
For the first verification test, we used dimensional analysis to ensure that all the disassembled parts of the device can fit into the carry-on suitcase, and the overall weight was 21 pounds, which was less than the 40-pound requirement, thus meeting the portability requirements. And in this image, A is showing the disassembled parts, and B shows the parts organized into the suitcase. For verification test 2, we verified the height adjustability of the device using dimensional analysis testing as well. And this is important to allow the alignment of the sensors to the humerus during measurement or data acquisition. So the results showed that the maximum and minimum height meet the range of the specs of the requirement. And we have that 40 inches is the max because any higher than that would cause the device to be unstable, and any lower than 25 inches, in that case, the handle would interfere with the base.
So for verification test 3, this was done to test the mechanical stability of our new base design. So in figure 19, you can see where we added 31 pounds to each side of the device to ensure that it could meet the specification of withstanding a horizontal load of 45 newtons. And we concluded that this new base design passed this verification test.
In test 4, we verified the accuracy of torque measurement. To get the measurement, we first placed the device horizontally with the head hanging out from edge of a table. Then secure the bar handle side with pin and applied weight on the strap handle side at location R equals to 4 inches to measure the torque. For each weight, we took 3 torque measurements and averaged them. The theoretical value is calculated following the equation T equals to R times 2F times 2 sinus 90 to verify the measurement. Here is the result. You can see for each torque being applied, the percent error is less than 5%. The device is quite accurate in torque measurement and met to our requirement. In addition, standard deviation are low, meaning that the device measurement keep consistent in use. And this is a graph comparing the two datasets. The orange line refers to experimental values, the blue line refers to theoretical. You can see the errors between the two lines very small.
For the angular displacement verification test, the IMU, the system, the gyroscope, and the accelerometer are calibrated. Then the handle is locked upright, and this is determined as 0 degrees. The handle is moved to plus or minus 90 degrees, which is right or left, and also to 180, which is when the handle is pointing downward. 3 trials are measured for each angle. The top table is the OIMU, where it did not meet the requirement of accuracy. You can see that the percentage error is greater than 5%. And interestingly, the right side angle of 90 degrees is off by 72%, where the angles are drifting away from the predetermined angle of 90. The bottom table is the new IMU data from with motion, where the percentage error is within the 5% margin required, and it was concluded that the new IMU is more accurate than the OIMU.
In summary, the device has met 5 of the 6 requirements. The entire device is portable. It has a height adjustable stand. It's considered stable during use. The torque and angular measurements are quite accurate with error less than 5%. However, the requirement 6 is not met yet. We still need to figure out a way to display the stiffness precisely.
The lessons learned and future revisions. So we were able to complete the redesign of the mechanical base We completed the verification testing for requirements 1 through 5, which were all met. We were able to meet with Dr. Thomas to test the device on a team member, where we received additional feedback on the final version of our device. We introduced a new IMU, and we used it to verify the accuracy of the torque and angular displacement measurements. A lesson learned was the importance of planning and effective communication, especially with everybody being remote right now. Future revisions, we did have one unmet requirement, number 6, which was the integration of the torque and angular displacement data together to output the stiffness. But overall, this device has a potential to have a large effect on the recovery rates of athletes and the prevention of injuries, which could also possibly shorten or lengthen an athlete's career. This device could also be used in the future, expanded to things outside of sports, such as frozen shoulder, which is common with people with diabetes type 2. So these are our citations. And we just have an acknowledgement for Dr. Sarver, who advised our group, and Dr. Thomas, who provided continual user input and feedback throughout the project, as well as all the senior design instructors who provided us with helpful feedback. Thank you. Any questions?
Contribution slides, Team 17. My name is Namni Nguyen, and my concentration is biomaterials and tissues engineering. For the senior design, I worked on the base design and the locking mechanism for the base. I also contributed to the work of the sensors for the IMU and the torque where I did a lot of debugging on the software part to in order to get the software to be able to input the data, convert the data into MATLAB, and calculated the input data. The most challenging part of the project was probably the communication between team members, however, we were able to solve that problem by talking internally and with the help of our advisor. And from what I learned is that the project, from the project is that you need to able to communicate effectively, and because of this, we were able to get the device back to the team members and continue to work on it. The next step for my career is that I learned how to communicate effectively, and also my plan for the future is to work in the industry.
Hello, my name is Han Trong, and although a lot of our roles intertwined during this project, my key accomplishments include conducting background research on the medical need, which includes setting up and preparing interview questions for our user need. I assisted in drafting the torque and IMU verification tests, as well as worked on data analysis for the results. The most challenging problem was definitely software, since it feels like we've been learning different aspects of design in parts through our time in college, but in this senior design project, we really incorporated everything we learned. Specifically, I had to learn to work with Arduino in order to understand and then make progress on what was already accomplished for this STROM device. I am currently applying to jobs in industry, as I learned that my interests include medical devices, data analysis, and project management. I'm super grateful to have completed various co-ops and all that I've learned from Drexel, and I feel that it has really prepared me for my next career steps. Thank you.
Joy Chen. My concentration is biomaterials and tissue engineering. In the senior design, my key accomplishment is researching, like research on the sensors or circuits we connect and the existing solution for the device, and also research on the torque cells and how to calibrate and verify the torque. But the way I research was too complicated. We didn't use that method to test. The most challenging problem in this design, I think, is the distance. Because of the COVID-19, we most of us just stay remotely. And I'm international student. I have a time delay in communication with my team members, and also hard for me to physically present for a device. For the next step, I will continue to study on biomedical engineering, and then we work on like company or industry that related to this major.
I'm Andrew Rockfeller, and my concentration is biomaterials and tissue engineering. My key accomplishments for this project include redesigning the base of the device and assisting with the verification test for the torque sensor. The most challenging problem with this project was working with an existing device. We had to figure out where the project had last been left off at, and we had to also figure out how the sensors had all been connected to the Arduino. And this included researching the sensors to learn how they communicated with the Arduino and MATLAB code, which was important for being able to understand and fix any problems with the code. My next career steps are to continue studying, and I have an interest in pursuing research.